Hello, folks. So, continuing where we last left off in Chapter 14. Now we will look at the difference between differential and integrated rate laws. What does one mean? So now that we've found out how to find a rate law for an overall equation, how can we apply that altogether? Apply that in a way that's a little bit more meaningful. So the first thing we need to consider is a differential rate law. The differential rate law, which would be something we learn about in Calculus 1, looks at the rate of change with respect to the concentration over time. So we have a change in A, a small d of A, over a small d of t. The change in concentration of A or change in time with respect to the concentration of A. So we're doing a differential. So we're looking at a rate of change. Now, that's something we directly found. We've experimentally determined. We've looked at that. Well, calculus allows us to do one step further, and that Calculus 2 teaches us about integration. If we do an integration where we look at how the changing time changes concentration, we can turn this equation using an integral into an equation that more closely resembles a linear format, such as y equals mx plus b. You can find this and relate this between two different concentrations at two different times. And by using this, we can learn a lot about our system. The integrated rate law is far more useful than the differential rate law is. However, we usually need to find the differential rate law first. So I need to look at these reactions with respect to each order individually. Now, a first order reaction, remember, only depends on the concentration of one component, saying that this atom will break apart or react with itself, and it's only a direct correlation that this atom shatters. Once this atom shatters, breaks, whatever, it can react with everything very, very quickly. When we get to Chapter 20, we will look at nuclear reactions. Nuclear reactions always follow a first-order decay mechanism, meaning that the rate of decay directly depends on just the concentration. That we can't speed it up, can't slow it down. It's just this guy decays at a constant speed. Not really changing, just it breaks apart, breaks apart, breaks apart. So with that in mind, when we look at our differential rate law, we integrate this. So when we integrate this, I'm going to wave my hands. I can show you the integral, but you don't really need to know the integral. But needless to say, I'll go ahead and show just a briefness real quick. Just real quick, and then we're going to wave our hands. If you don't know any calculus, you're not going to get too far, but it's the negative d sub a over d sub t equals k a. So we get the t to one side and the a to one side. So we get that over here. So we have 1 over a d sub a equals negative k d sub t. We're going to integrate this from t equals 0 to t equals, we'll just call it t1. Well, we're going to integrate this from concentration at the 0 point to the concentration at a time t. Well, the integral of 1 over x dx, the sum of this is ln x plus c. Well, so with that in mind, we're going to have ln of a sub t minus ln of a sub 0 on one side. The k is a constant, so that falls out. So when we integrate, if we integrate 1 of x dx, this is just going to give us x. So this is going to get t minus t at time 0, which is just going to be 0. So our equation simplifies to ln a sub t over a sub 0 equals negative kt. That's integration for you. If you don't know how to do it, don't worry. You don't have to know how to do it. I give you this equation. I never ask for you to know that equation, to memorize that equation. But so this relates two concentrations with the time period it takes for that to change. Now, if I just graph the concentration versus time, we get this little curve. Whoop. But if I graph the concentration, the ln of concentration versus time, I get this nice little linear curve right here. So if ln of the y is the y-axis and t is the x-axis, I can get this straight little y equals mx plus b. The b is our natural log of the initial concentration. Well, what's more, is because this is linear in such a way, we can calculate the time it takes for half of a given concentration to decay or react. So it doesn't really matter what a sub 0 is, because a sub t is half that value. So if a sub 0 is 10, a sub t is 5. If a sub 0 is 30, a sub t is 15. And so we can get a fraction that says 15 over 30, which is essentially 1/2. ln of 1/2 is equal to negative k t for that given 1/2. So this can simplify into this nice little equation. Now we're doing a little math-magic here, but ln of 1/2. I can flip this by flipping the sign, taking that negative to the other side, flip that to be ln 2 over 1. 2 over 1. And so we can simplify this to say ln 2 over constant k is equal to t 1/2. But what makes first order decay so devious is the time it takes, or half of it, to decay is always the same. Always the same for a given temperature. So if it takes an hour for 50% to go away, so it would go from 100% to 50%. It takes another hour to go from 50% to 25%. And it takes another hour to go from 25% to 12.5%. When you're talking about nuclear decay and we need this to go down to minuscule amounts, this is where it becomes incredibly problematic. Now, zero order mechanism is one where it does not depend on the direct concentration. So this one is all, when I integrate this, it simplifies into a simple y equals mx plus b. The slope of the line, looking at the two concentrations, is the negative k. If I try to graph it any other way, you're not going to get a nice line, but only with the change in concentration versus the change in time to get this nice little graph. Now, it also has a half-life, but because of the fact that it's not a division, it's a fractional amount, the half-life is dependent on the amount of a sub 0 we start with. So depending on the half-life is constantly decreasing, because each time we go through a half-life, it's just like if it takes an hour for 50% to decay, it's going to take 30 minutes for it to decay from 50 to the 25, and then it's going to take 15 minutes to decay from 25 to 12 and a half, and it's going to just keep dropping down like that, because it does not directly depend upon the concentration of A. So it's going to drop. So technically, after 2 hours, it would all be gone. But so you get a nice little equation like this, but it depends on how much concentration of A we have. A at times 0. The last one, our second order reaction, is a quadratic relationship between the concentration and the rate. For when the concentration doubles, our rate quadruples. When the concentration triples, our rate non-tuples, something like that. But it's always the square. Now, running our calculus through, it becomes a little bit more complicated. Of 1 over the concentration of A minus 1 over the concentration of A at time 0 is equal to positive kT. So with that in mind, the linear graph becomes 1 over A sub t equals kT plus 1 over A sub 0. So graphing this, just the straight up concentration versus time, gets this ugly little curve, not too dissimilar from first order. But when I plot this, 1 over A as the y-axis, we get the nice little line. Finally, the half-life of this. Once again, since this is a subtraction and not a straight up divisional fraction, our concentrations will not cancel. So it once again depends upon our concentration. So after waving our hands a little bit with the math, you get that the half-life, the time it takes for half of the concentration to decay, is dependent on 1 over a constant times the initial concentration. Meaning, the bigger the initial concentration, the shorter your half-life. But that means as it decays, it's going to slow down. So the time it takes for half to decay will take longer and longer as it goes, because it's second order. There's less of it to go around, so it's less of it to bump into A, so it's not going to react as fast. So with that in mind, we have 3 sets of examples. We have a 0 order with a half-life of 20 seconds when A sub 0 is 0.9 molar. What would be the concentration after 35 seconds? So let's look at that. We're looking at the change in concentration with time. Logically, you should know what a reasonable answer is. If the initial concentration is 0.9, 20 seconds, half of it's going to decay. So after 20 seconds, it's going to go down to 0.45. Now, another 20 seconds and another 0.5 would go away. So 35 seconds is a little bit shorter, meaning it's going to be very small concentration left, but there will be some left. Now, our 2 equations are K times A sub 0 equals T1/2 and then a sub t minus a sub 0 equals negative kt. So we have a sub 0, we have t, but we don't have k. So in order to have k, we're going to use and solve for this guy. So k times 0.9 m equals 20 seconds. So to solve for k, we're going to divide 20 seconds by 0.9. K is equal to 22.2 m per s. Now we're going to plug this into here. A sub t minus 0.9 is equal to negative 22.2 m per s times 35. 2.2 times 35 seconds is going to be I think I did something wrong. I think it must have been k over a sub 0. K over a sub 0. And once again, oh no, it's my bad. It's a sub 0 over 2k. So you'll notice, how did I notice I did something horribly wrong? It was really easy, because 777, when I did that math, suddenly I would have had more concentration than I started with. So, that quickly shows. So a sub 0 over 2k equals t1/2. Well, rearranging that, a sub 0 is 0.9 divided by 2 times 20. 0.9 divided by 0.9 divided by 2 divided by 20. It's actually 0.0225 m per s. I'm a fool and I know it. So a sub t equals negative kt plus a sub 0. So a sub t equals negative 0.0225 m sub s times 35 plus 0.9. So you'll notice this number will not be negative when all said and done. 0.0225 times 35 is negative 7.875. Now I add 0.9 to this, and the amount of sample I have left is 0.1125 m. A number that is greater than 0, but far less than half. And that should make sense with a zero-order reaction. It's chugging along at speed. So, that's the first one. That was my bad, my mistake. And with that in mind, first order reaction, a half-life, better write the equation right this time, half-life of 5 minutes. T1/2 of 5 minutes. How long would it take to decay 25% of the starting material? So we want a sub t to be 75% of a sub 0. At what time would that happen? Now, in order to avoid confusion, I'm setting it up that way. Now, because this, because of how this is set up, we don't care how much a sub 0 is. First thing, we almost always need to find our k. So we're going to take ln of 2 over 5 minutes. It's okay that it's 5 minutes. I don't need to turn this into seconds. I'll just have time in units of 5 minutes. So ln of 2 in parentheses to make sure it's, I don't want 2/5, I want 2. So our ln of 2 divided by 5 is going to be 0.1386 inverse minutes as our time, as our k constant. Now, we want 75% left. So natural log of 75%, if this is 100%, is equal to negative k sub t. So ln of 0.75 equals negative 0.1386 inverse minutes t. So ln of 0.75 is a negative number, negative 0.2876. So that's negative 0.2877. I'm going to round that. And when I divide that by the negative 0.1386, I get the time it would take is 208 minutes. And that should also make sense. That should also make sense because if half-life is 5 minutes and it slows down as it proceeds, well, how long would it take to get a quarter life? And the quarter life would definitely be less than half of the half-life. So the first 2 minutes or so, it's going faster, and then the last 3 minutes, it's slowing down. And the last question for this, just showing all the examples of these equations. If a reaction took 45 seconds to decrease from 1 molar to 0.3 molar, what is the rate constant? T1 m to 0.3 m. We have 1 over a sub t equals kt plus 1 over a sub 0. So with that in mind, we might not even need our standard equation. So we can just do this. Okay, with that in mind, we have a sub 0, we have a sub t. We can just say 1 over 0.3 equals k times 45 plus 1 over 1.0. So let's start by saying 1 over 0.3 minus 1 over 1. If I do that, I'm going to get 2.33 equals k times 45. Now if I divide both sides by 45 seconds, I'm going to get a k. The k is going to be 0.05185 1 over ms. That is it. The trick here is recognizing what equation we need and identifying variables. Once I've identified my variables, it's just a matter of, can we plug these guys in and solve? If you can do that, it should be simple at that point. Now, the last problem I have before I finish this video is, well, let's look at what order of reaction is this based on linear plotting of the data. In set 1, I have plotted the concentration versus time and tried to put a line regression through it. Natural log of the concentration versus time and put a linear progression through it. And the 1 over concentration versus time. See, which one does the line fit? The line fits the natural log. So the K constant would be .24. Now the second set of data, I've plotted the linear regressed it, and the concentration versus time not linear. The natural log of concentration versus time not really linear. It's close, but not quite there yet. But when I plot 1 over the concentration, suddenly we have a linear regression. And so 3.5 is our K constant for that. But that's where I'm going to stop and leave you. I thank you for your time. When we pick up next, we will look at the Arrhenius equation for these guys.